So we're going to start with the first piece of our introduction to organic chemistry with our simplest functional group, alkanes. So this will be in the section under hydrocarbons. And with alkanes, structures where there are carbon-carbon single bonds, and the octet for carbon is fulfilled if not bonded to another carbon by just simply being singly bonded to hydrogens. So it's carbon-carbon single bonds, and the octet is fulfilled by fully saturating these carbons with hydrogens. And so what I'd like to cover in this video is just the general structure. And so in general, we have a carbon with a little N down the bottom there for however many carbons are actually in your structure. And then in the molecular formula, we'll write the hydrogen. And the number of hydrogens is equal to 2N plus 2. And you'll see why the plus 2 in a second. The carbons are sp3 hybridized. So sp3 hybridized carbons. The electron geometry is going to be tetrahedral. When we do chemistry on an sp3 hybridized carbon, that tetrahedral geometry will become very important to us because when we move into other functional groups, so out of the hydrocarbons, so aside from alkanes, when there's other stuff on those carbons, other substituents bonded to the carbons, the size of those other groups, or even if we have a larger hydrocarbon substituent, like a big bulky alkyl group, the size of those groups is going to become important because of this molecular geometry and the type of chemistry we can do on those particular carbons. So for example, we can start out with something that has 4 carbons. So we'd have a little 4 down here for N. H would be 2N plus 2, so H10. We have a condensed structure that we can draw. And that's simply going to be where we line up all of the carbons, and we're going to put those little hydrogens, however many there are, on each carbon in the condensed structure listed right after the carbon. So in other words, this last carbon here on the chain is going to have 3 hydrogens, and then it's going to be bonded to another carbon. So we'll put the carbon with however many hydrogens are on that particular carbon. Then we're going to follow it in the condensed structure by the other carbon in the chain. And we'll do the same thing for that carbon. This one will have 2 hydrogens, another carbon with 2 hydrogens, and then the final carbon with 3 hydrogens. So again, these hydrogens are fulfilling the octet, fully saturating all the carbons, right? If we were to draw the expanded structure, you can actually see where these hydrogens are going to fall on the chain. So the expanded structure, the larger these get, the less exciting it is to draw the expanded structure. But for a small molecule like this, it's no problem. The easiest place to start with this, and let me just move this down so that we can get some space, is to start out by drawing your longest continuous carbon chain. And that is going to be a little term that becomes pretty important to us when we move into nomenclature as well. So naming these molecules, you're looking for your longest continuous carbon chain. So when you build these structures, you're going to do the same thing. And this will just be the skeleton for your molecule. So carbon is going to be bonded to another carbon, bonded to another carbon, and to the 4th carbon. So you're just writing out your little scaffold right there. Each one of these carbons is going to be fully saturated, fulfilling its octet with hydrogens. And that's where these other single bonds are going to come in. So I'm going to put a hydrogen in each of these spots to complete the octet for each of the carbons. And you can see the 3 hydrogens on the end versus the 2 hydrogens for each of the interior carbons. So that's where that 2n plus 2 comes from. So in order to get a complete octet on those terminal carbons, we have to put an extra hydrogen on each. So Cn and then H2n plus 2. So of course, we're not super interested in drawing the expanded structure for all of these molecules, especially the more complicated they get. So very often you'll see these written as the condensed structure. Sometimes you might also see this. This is reminiscent to me of like a shorthand electron configuration. So for a small molecule like this, you might not feel like this is necessary, but you could put these CH2s, by the way, these have a name. We call these methylenes. You can put these methylenes, and however many there are, so we have 2 here, in parentheses, a little 2 on the outside, and then put the last methyl group. So pay attention to this terminology as I'm going through it, because I'm sort of emphasizing these words for a reason. These little CH2s in here are called methylenes. And so when I just casually refer to, hey, the methylene at blah, blah, blah position, like you know what I'm talking about, right? And those end carbons, those are called methyl groups. Alkyl groups are like if you take the molecule, just the regular alkane, so that if it was CH4, it would have been methane, and you remove one hydrogen and put a bond to like the rest of the molecule, that methane becomes a methyl group. So that terminology is something you might want to put in your back pocket as well. So again, you know, for something as simple as this particular molecule, which by the way is called butane, so we have prefixes for all of our different numbers of carbons in the chain. This but means 4, so this is butane. And as you can see, there's not a ton of methylenes in this chain. If you had something larger and you didn't feel like writing out all those CH2s, the parentheses are a nice little sort of shorthand. So we have within this category of sort of general structure an introduction to constitutional isomers. And we have different types of isomers. Iso just means same. So these are going to be molecules with the same molecular formula. So I'll just write MF. So in other words, C4H10, right? But different arrangement of the atoms. Or groups, I guess, as the molecule gets bigger. So with butane, there's not a whole ton you can do with butane, but as you add carbons, you increase the number of different constitutional isomers exponentially. So I'm going to go up 1 carbon and show you pentane. So that would be C5, H12. In our first example, we could draw the condensed structure, and that would just simply be CH3, CH2, CH2, another methylene, and then the 5th carbon with its 3 hydrogens. So there's your condensed structure. Or you could draw it like this, CH3, parentheses, there are 3 methylenes, so I'll put a 3 outside the parentheses, and then another CH3. dot, dot, dot. Or you could draw what we call a line bond structure. So I'm not going to draw the expanded structures for these. It's not really necessary. Occasionally, when we're moving groups around, so for some of these isomers, I will put the bonds in. But for the most part, if we're just drawing like a straight chain, it's easier to just, write the CH3, CH2, CH2, whatever. And then for larger molecules or more complicated molecules, this can get a little tedious. So we have what's called a line bond structure. So with a line bond structure, each point on a line is a carbon, and all of the hydrogens are simply implied, meaning I'm not going to draw them in, but you just know that they're there. If it's a carbon that's not bonded to a hydrogen, say it's bonded to an oxygen or a nitrogen or whatever, you would write that symbol in. So I'd put an O or an N or a P or whatever. But for hydrogens, they're just implied. So in other words, instead of CH3, CH2, 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 CH3, I could write a line like this. So each point of that line is a carbon, and the hydrogens are implied, right? So there's two carbons there. So 1, 2, 3, 4, 5, right? So I can number these just this first time so you can see what I'm talking about. There's one carbon, there's the second carbon, there's the third, there's the fourth, and there's the fifth. And by implying the hydrogens, it means I'm not going to put the H's in, but you know that carbon has 4 valence electrons, and it has a tendency to bond covalently, right, using all 4 of those valence electrons. So pentane would have 12 hydrogens, and you would know just by looking at this line bond structure that each one of those carbons octet would be fulfilled by fully saturating it with hydrogens. So we don't write the H's in. I can rearrange this particular molecule. So I can take a group and I can essentially move it. So if I wanted to take one of the methyl groups on the end and just move it in one carbon and swap it out with a hydrogen. So I have another, what we call constitutional isomer. So I'm going to take that first condensed structure you see in the first example, and I'm going to move the outermost methyl group, and I'm going to put it on another carbon, but I need to swap it out, right, with a hydrogen, because you can't have 5 bonds on a carbon, or in other words, we're not going to put 10 electrons around carbon. If I do that, I have a new methyl group on the end. So in other words, if I took a hydrogen off of, say, this carbon, and I were to put it, say, on this carbon, I now get this methyl group. And why would I do that? Because I'm going to take this methyl group and I'm going to put it here. So one of the hydrogens that you see on that particular structure, right, the one on the third carbon that you're looking at, is going to get moved over to what you're staring at as the second carbon. And I'm going to take that methyl group on the end and I'm going to move it over here. So I get this molecule. So let me erase all this stuff and we'll number these so that it maybe makes a little more sense. If this is carbon 1 and this is carbon 2 and this is carbon 3, what I'm saying is I'm going to take a hydrogen off of carbon 3, I'm going to put it onto carbon 2, and I'm going to take that methyl group off of carbon 2 and put it on carbon 3, right? So this used to be that carbon. It's now carbon 1 in this structure, right? And then I'm going to take the methyl group and I'm going to put it on that carbon. This right here is this right here. So hopefully that was easy enough to follow. You're basically going to take a group and move it over onto another carbon, swapping it out for a hydrogen so that you don't violate the octet for the carbon. I can draw the line bond structure for this, and that would look like this. So I've got 2 carbons there. So I've got 1, 2, 3, 4 carbons, and I have a methyl group coming off of the second carbon. You might be saying to yourself, well, why couldn't you just take the methyl group on the end and move it 1 carbon in? And you can. I could have drawn something like this. So I could have said, well, I'm going to make the swap on the other end. But those molecules are identical. And the line bond structure for that would be this. So those are not isomers. Those are identical. So these are the same. But these are isomers. They have the same exact molecular formula, but we've just arranged them differently. There's a third one that we can draw for pentane. If I move 2 methyl groups, and I draw something like this, so again, I'm swapping hydrogens out for these methyl groups. I still have C5H12. I've just arranged these differently. And I have this. So these are all isomers, all 3 of these are considered to be constitutional isomers, meaning how these things are put together. We can have ring structures. We call these cycloalkanes. And their general structure is CN, H2N. In order to form a ring, we need to bond 2 of the carbons together. And if you're going to do that, you need to remove a hydrogen from each so that you don't violate its octet, right? So for example, I could have something like C6H12. I'll draw the expanded structure, and then I'll show you, this is a good moment to show you why the line bond structure is preferred. So I'm going to take 6 carbons, and I'm going to join them together in a ring. So I've got a hexagon that I'm going to form. Hex, again, is our prefix for 6. So I've joined all of those carbons together in a ring. Instead of drawing out a straight chain, right, I have connected the 2 end carbons, and now I'm going to fully saturate these carbons with hydrogens. So I'll just draw the bonds in first, and then we'll put the little H's. You probably right now see why we would prefer to draw the line bond structure for these. And this isn't even really a complicated molecule, but you can already get the feeling for how annoying it would be to keep drawing the expanded structure. Okay, so each one of these carbons, again, sp3 hybridized, there's a tetrahedral geometry about them, each individual, right, carbon. Or you could draw the line bond structure, and it's simply just a hexagon, right? So that's a lot easier than drawing out the expanded structure. The hydrogens are all implied, all the carbons are linked together. We've lost that 2n plus 2 because we've linked up 2 of the end carbons, right? And so in order to do that and not have these carbons be hypervalent, then we have to eliminate 2 of the hydrogens in order to form the bond. What happens though, so we're looking at just simple examples of these things, right? Like we've got pentane here, we had butane up here. We have a cyclohexane, right? So that's how we would name that. We'll get into nomenclature in a second. But what happens if you have a molecule like, say, for example, cyclohexane, and it has something attached to one of the carbons, like there's a substituent, or in other words, another group attached to one of the carbons? And what if that group just happens to be another hydrocarbon group? Like it only has carbon and hydrogen bonded to it. So we should probably go through how we would name these alkyl groups. So for hydrocarbons, we have alkanes. In the next couple of videos coming up, we will have things called alkenes and alkynes. In the Gen Chem review, we were talking about an introduction to the functional groups. All these hydrocarbon groups in general, right? Alkanes, alkenes, and alkynes can be turned into substituents. They don't have to be sort of the star of the show, or in other words, they don't have to be the parent molecule. They can be part of the parent molecule. If they are part of the parent molecule, we remove the ane, the ene, and the ine, and we say, let's add YL to that and call it an alkyl group, meaning I've got a group that only contains carbon and hydrogen. What we're going to do is we're going to take away one hydrogen of an alkane, or you'll see in another video an alkene or an alkyne, any group, right? We're going to remove one of the hydrogens from that parent molecule, and we're going to attach what we're going to call an alkyl group. And we have names for these things. We're going to attach that alkyl group to another molecule, or to that parent alkane, and we're going to call it a substituent. So group, substituent, that kind of thing. That's shrubbery sometimes if it's the rest of the molecule and you don't care about it. Like, call it what you want, but if you hear that word substituent, we're talking about it's another group attached to a parent molecule. So a very simple example would be like if we had methane. We're going to remove a hydrogen from methane. So let me write this name here, because this will be important for naming the substituent. So that is the molecule methane. When we remove a hydrogen from methane and attach it to what we're going to call the rest of the molecule, and I'm just going to label it R, it goes from CH4 to CH3, and then the bond, we'll draw a little stick there. Now, in organic chemistry, we have that little H3 there, but we know as we're going through, this is how we draw basically the bond between the carbon and the rest of the molecule. So that stick is saying I'm a carbon bonded to the rest of the molecule. So where R equals rest of molecule, and the hydrogens are actually bonded to the carbon. So it's just the way we happen to write things. So in other words, those hydrogens are not bonded to R. I know it looks that way in the molecular formula, but it's not. And this CH4, having lost a hydrogen, is now just a substituent attached to the rest of the molecule. And this is going to be a methyl group. So it goes from being methane, where it's the star of the show, it's its own molecule, to being a methyl group that's attached to some other molecule, some other parent molecule. So let's look at another example. I can have butane, regular old N-butane. And by the way, if you're wondering, N, this little N-butane, that little N stands for normal, which, there's no such thing as normal, but in organic chemistry, when you see that little N, it means it's just the straight chain. I can remove a hydrogen from one of these terminal carbons, so one of these end methyl groups, and I can turn that whole thing from an N-butane to an N-butyl group. So I can say that I've got this. See how we've removed a hydrogen there from that N carbon? It's going to be attached to some other molecule. And this is now called an N-butyl group. So because butane has enough carbons to form a constitutional isomer, I can write out that constitutional isomer. Imagine I were to take one of those terminal methyl groups and I were to swap it over for a hydrogen on one of the interior carbons. And I drew something like this. So again, same molecular formula, different arrangement of the atoms. So now, if I want, I can take away a hydrogen from one of those end carbons. So here we have what's called isobutane instead of N-butane. I have an isomer of butane. And, there's only 4 carbons, so that's not, we call this isobutane. There isn't much else you can do in terms of drawing other constitutional isomers for something this small. But isobutane does exist. It is an isomer of butane, and we can take a hydrogen off of one of those terminal methyl groups and attach an R group to it. So I can have a group like this, and then this could be attached to something bigger, and then that group would be considered an isobutyl group. There is another option in this particular case. So you can only make one isomer for this molecule, right? There's 2 constitutional isomers, but I have like one option here to make an isomer from N-butane, and I can get isobutane. If I'm allowed to deprotonate one of the terminal methyl groups, it's totally fine that I could also take the hydrogen off of the interior carbon. And if I do that, then I have isobutane, and it's this carbon that I would take the hydrogen off of, that middle one. It does, by the way, make a difference. If that's going to be the group that's bonded to R. So I've got something like this. Now instead of that hydrogen, I have an R group. That particular alkyl group is what we call a tert for tertiary butyl group. Or sometimes you'll see T-butyl. So now seems like a pretty good time to tell you about how we classify carbons. So up here, and this is I guess a good example to use because there's only a few isomers. In N-butane, if we're talking about this carbon, So that methyl group on the end has, if you were to consider the two methylenes and the methyl group that come before it in that particular condensed structure to be R, and you're looking at a carbon that has R plus 3 hydrogens attached to it, we have what's called a primary carbon. In other words, it has one R group and 3 hydrogens. So imagine that CH3, CH2, CH2 equals R in that case. That's a primary carbon. Down here, if you were to imagine each one of those methyl groups is an R group, and then that carbon is attached to just a hydrogen and those 3 R groups, we have 3 R groups, so a tertiary carbon. So that's where that tert butyl comes from. So we have a primary carbon there, we have a tertiary carbon. As we move through the other functional groups, specifically with alcohols, when we classify alcohols, I will remind you, hey, there's a primary carbon, there's a secondary carbon, and there's a tertiary carbon. What I'm talking about is how many R groups are attached to that carbon. Or you could view it from the flip side and be like, okay, how many groups that are not R groups are bonded to the carbon? So with the alkanes, it's easy to see. It's like, okay, I'm talking R groups versus hydrogens, right? You can see that if you are trying to do chemistry on whatever R is, and it's got a tertiary butyl group attached to it, and that carbon that may be bonded to that T-butyl group is sp3 hybridized, that T-butyl group is going to take up a lot more space than an isobutyl group, which would take up more space than an N-butyl group, right? So this molecular geometry becomes important to us as we get a little more congested around the site where we plan to do chemistry. So just keep that in mind as we move through. If you have a cyclic compound, so same deal, I could have say, like we just did cyclohexane, so I'll do our little cyclohexane molecule. Imagine removing one of the implied hydrogens. So pick your carbon, it doesn't matter, they're all the same, right? We're going to take a hydrogen away and we're going to replace it with R for rest of molecule. This right here, when it's attached to another bigger piece, right, another parent, is going to be called, instead of cyclohexane, a cyclohexyl group. And we can do that for any of the ring molecules. So I could have a 3-membered ring, and I'm going to take away a hydrogen from one of the carbons and just put an R group. This right here went from being cyclopropane, so prop is our prefix for 3. This now becomes a cyclopropyl group. So let's just move into nomenclature, because I keep referring to these molecules by their names and we haven't quite gotten there yet. So it's important to learn the structure before we learn the nomenclature so that you can tell like how these things are put together, and the fact that constitutional isomers do exist. And by the way, the physical properties of these different isomers are going to be different. So if you imagine that these molecules only have dispersion forces, right, because there's only carbons and hydrogens, the boiling points of N-butane, isobutane, and tertiary, isobutane and N-butane are not the same. And then a molecule that would have a T-butyl group, an isobutyl group, and an N-butyl group would also not be the same. They only have dispersion forces, right? It's just carbons and hydrogens, and there's not a huge difference in electronegativity between carbon and hydrogen, so there's not much polarity going on. But if you arrange these groups differently, like get them a little bit more clustered, it makes it a little more difficult to polarize the electrons. So you can expect that something with a T-butyl group, depending on what that something is, if we keep R the same, you can expect that there isn't going to be much of an increase um, in the boiling point if we cluster up the groups. In fact, N-butane should have a higher boiling point than isobutane because it's easier to polarize the electrons in that straight chain. Once we start moving groups inward and clustering things up, it just makes it a little more difficult to create that instantaneous dipole. So these do affect the physical properties a little bit. In terms of how do we name these, the nomenclature of alkanes is actually kind of a big deal because the nomenclature for every other functional group that comes after this is going to follow the same rules. And very often, one of the rules for naming a different functional group would be, like if we were going to name an alcohol or something like that, or an amine, we would say, hey, you're going to follow the same rules as you would for naming an alkane, but you're just going to change the suffix. So this particular sort of set of instructions for naming these molecules for alkanes is going to be pretty important to learn. We have two different systems. We have what we call a systematic system, and then we have what we call a common system. Common names are things like acetic acid, right, for a carboxylic acid. If you're, talking about something that's commonly used, but acetic acid being the common name for that particular molecule is not its systematic name. The systematic name is nice because it's sort of like you can't get it wrong. If there's other groups that are attached to the molecule, we have like a numbering system that sort of like acts as the postal address on the molecule for whatever group you're talking about. And that systematic nomenclature is otherwise or also known as the IUPAC system. The very first rule is to find the longest continuous chain of carbons, and I'm going to abbreviate that LCC. So we're going to find the longest continuous chain of carbons, and we're going to call that the parent. And for alkanes, we're going to add the suffix ane. So this is where you're going to follow the same set of rules for all the functional groups. For alkanes, the suffix will be ane. Ane tells you that you have carbon-carbon single bonds, and if there's anything that's bonded to one of those carbons and it's not a hydrogen, with the IUPAC system, you will count the longest continuous chain of carbons and you will give that substituent the lowest number. So in other words, if I've got a molecule like hexane and there's like a bromine bonded to the second carbon in, I'm going to call that 2-bromohexane, right, and not 5-bromohexane. So what we are referring to is giving that substituent priority by giving it the lowest number. So to start, we need to go over the prefixes that we're going to be using. So that longest continuous chain is going to be the parent, and that parent is going to be indicated by a prefix. So if I've got 6 carbons in the chain, the longest continuous chain, then the prefix would be hex and the suffix would be ane. So hexane, right? We'll just do 1 through 10 here. So 1, Oops. All right, I'll put the 6 over here. All right, we'll just do 10 here. There's a table in your textbook that will give you more numbers and prefixes than this, but we'll just do 10 carbons. So these numbers refer to the number of carbons in the longest continuous chain. If you have 1 carbon, the prefix is meth. So if you had an alkane with 1 single carbon, we would call it methane. 2 carbons is eth. 3 is prop. 4 is bute. 5 is pent. 6 is hex. 7 is hept. 8 is oct. 9 is known, and 10 is dec. A lot of these are easy to remember because they just follow regular old geometry, right? So 1 carbon meth, so if you have an alkane, it's methane. 2 carbons eth, you have an alkane, it's ethane. If I had an alkene, I would change the suffix. It would no longer be ane, it would be ene. I'd have ethene, right? So this is a UPAC system, right? Second rule that we're going to follow is if you have substituents, so if there are groups on your parent, so we call these substituents, so on the parent, or in other words, you count out the longest continuous chain and you notice that there's a substituent on one of the carbons. You identify the carbon with a number. And you're going to give priority, in other words, the lowest possible number. So I'll write that in parentheses. This will be the lowest number possible on the chain. To the substituent. And then you're just going to follow it up with the suffix for the alkane. So this is easier to see than it is to hear, I think. So let's do like something like this. We'll put a substituent here. We'll keep it simple, and since we just learned alkyl groups, we'll make that a methyl group. Okay, so what you're going to do is you're going to find your longest continuous chain of carbons. So you can count from the left or you can count from the right. If I count from the left, this is carbon 1, 2, 3, 4, 5, 6. I'll change the color and we can count from the right. 1, 2, 3, 4, 5, 6. Now you might be wondering, like, why can't you go down into the methyl group? If I did that, I'll do it in a different color. We have 1, 2, 3, 4, which would make the propyl group the substituent, right? But notice if we count in that direction, we only have 4 carbons, right? If we count left to right across the top, we have 6. So you're looking for your longest continuous chain. So we're going to erase that. What if I counted from this direction? 1, 2, 3, 4, and 5. Again, I can count in a different direction that gives me more carbons. So my longest continuous chain is going to be counting just across the top. And now my option is to count either from left to right or right to left. You're going to follow, now you've identified that you have some kind of a hexane, right? So that's going to be the parent. I have 6 carbons, so we'll just take this one step at a time. 6 carbons, hex. I have an alkane, so the suffix is going to be ane, but there is a methyl group sort of like dangling off this thing, and we have to let someone know what carbon it's on. So the second rule that we're going to follow is to give that substituent priority. In other words, we're going to give it the lowest possible number. I could have numbered from right to left. I could have numbered from left to right. If I number from left to right, the methyl group falls on carbon 3. If I number from right to left, the methyl group falls on carbon 4. So I'm going to say that I have a methyl group on carbon 3. And I'm going to put all of this together. And I'm going to say 3. So that's going to be the carbon that the substituent is on. I'm going to separate the number from the rest of the name with a hyphen. So this is a UPAC system. 3 methyl, because that is a methyl group. It's an alkyl substituent. It's not methane. We've removed a hydrogen. And that hexane is R, right? That's the rest of the molecule. So we're going to tell somebody we have a 6 carbon chain, fully saturated, single bonded carbons. So we have a hexane. We have an alkane, right, with 6 carbons, and we have a methyl group on the 3rd carbon. So that's how you would name that. What if I had an example of a molecule that had more than one substituent on it? So say I have something like this. I'll get a ring, so we can get some experience naming rings. So there's cyclohexane. There are 6 carbons, right? But they're hooked up in a ring system. And I'm just going to put 2 methyl groups on here. So we're going to number the ring to give the groups the lowest possible numbers, right? If there's only one substituent on the ring, you don't have to use numbers, because if there's only one substituent on the ring, if there was only one methyl group on this ring, it's obviously carbon number 1, because you have to give your substituent priority. If you're giving it priority, you're giving it the lowest possible number. If there's only one substituent, it has to be on carbon 1, right? But since we have 2 substituents, one of those is going to be carbon 1, and then the other one could either be 1, 2, 3, 4, 5, 6, or it could be carbon 2. So you're going to, in other words, say I could number it in this direction. 1, 2, 3, 4, 5, 6. And say I've got 1, 2 dimethyl, or I could number it in this direction, and I could say this is going to be carbon 1, this is 2, 3, 4, 5, 6. So obviously, if we're giving priority to the substituent, one of those carbons has to be carbon 1. The other one's going to be carbon 2, right? Because we want to give that the lowest possible number. So again, we're doing this for your substituents. So if there's 2, right, and one of them is obviously on carbon 1, then the other one has to be on the next lowest number possible. And with a ring, I mean, I could have started with the other methyl group and called that carbon 1 as well. Just so you're aware, by convention, usually if it's something as simple as this, that top carbon at, like, if you imagine this to be like a clock, that carbon at like noon is considered to be carbon 1. It doesn't have to be that way, but something as simple as this, it just makes it easier to start at the top. So the way that we would indicate having 2 substituents and telling somebody what numbered carbon they're on is to take the numbers and separate them by a comma. So 1, 2. Then we're going to put a little hyphen, and we need to tell somebody that we have 2 methyl groups. The prefix for 2 is di, and then we're going to name the group. And then we need to tell somebody this is on a ring. So we use the word or the prefix cyclo. That ring has 6 carbons, so hex, and it's an alkane. So let's dissect this a little bit. We have an alkane, that's the suffix. It has 6 carbons. It's a ring. It has 2 methyl groups. And the groups are on C1 and C2, not C1 and C6. So that's how you can basically dissect the name. When you are looking at a structure and you're going to write the name, we write it from left to right. In my opinion, it's always been easiest to figure out the structure by reading the name from right to left. The far right, the suffix, tells you what functional group you have. So this is an alkane. If it was an alkene, it would be ene. If it was an alkyne, it would be ine. If it was an alcohol, it would be all, right? If it was a carboxylic acid, it would be oic acid. If it was an ester, it would be, ace. So it's like, 8, I'm sorry. It's the suffix tells you the functional group that you have. Let's do one where we have sort of like a line bond structure, and then I'll show you some common prefixes that we use. So common nomenclature uses prefixes like iso and tert and stuff like that. So let's go 2, 3, 4, 5, 6, 7, 8. Let's stick, say, like a chlorine on that carbon. Maybe on this one, we'll just do a methyl group. So notice there's just a stick there. That carbon at the end of that little, this thing right here, this little carbon on the tip like that, that's the end of a line. So that's a carbon, right? And the hydrogens are implied. So that's how you draw a line bond structure for a methyl group, right? Maybe on the next one we could do, oops, get the highlighter off here. We could do what would be called an ethyl group, right? So see here, there's a carbon, there's a carbon. The one on the end has 3 hydrogens that are implied to complete its octet. The one in the middle has 2. Okay, so we're going to number this. We could go from left to right here. Find your longest continuous chain. 1, 2, 3, 4, 5, 6, 7, 8. You could also number from right to left. If I did that, it would be 1, 2, 3, 4, 5, 6, 7, 8. Here's the deal though. You got to look at each one of your substituents and see which one is going to take priority. This is now we have different substituents. Before it was like 2 methyl groups. Before that it was 1 methyl group. Now I've got a methyl group, a chloro group, and an ethyl group. My longest continuous chain is 8 carbons. I think we could see that if we went down through the ethyl group, it would be 1, 2, 3, 4, 5, 6. So that's not our longest continuous chain. So some octane derivative is going to be our parent compound. So in other words, we could say our longest continuous chain is 8 carbons. We have multiple different substituents, right? So we have a new problem. So we have different groups. So what we're going to do in the name is we're going to cite them alphabetically. So it behooves you to actually realize what the names of these different substituents are. And we're going to give each one of those a different numbered carbon because they're all on different carbons, right? So we're going to name them alphabetically, giving the lowest numbers possible. So we counted out 8 carbons from the left to the right and from the right to the left. If we number this thing from the left to the right, we end up with, I could write this out in the 2 different colors that we chose. So we're going to start out with left to right. We've got a chloro group on the 2nd carbon. We have an ethyl group on the 5th carbon, and we have a methyl group on the 4th carbon. So I see that. So I've got a chloro group here. If I'm counting from left to right, it would be on carbon 2. I have a methyl group, and then I have an ethyl group. But C, right, comes before E, comes before M. So these are the groups. I've got chloro. I have ethyl. So again, this would be CH2, CH3. So that's that little group on carbon 5 in blue there. And I have a methyl group, which is a CH3. And if we're numbering from left to right, it's sitting on carbon 4. Now I need to alphabetize these. Obviously, we've done that in our list. So counting from left to right, I have 2 dash chloro. Then I need to tell somebody I have an ethyl group on the 5th carbon. So 5 ethyl dash. I have another substituent. Methyl comes after ethyl alphabetically, even though 4 comes before 5. So don't get confused with, hey, you put a 5 before the 4. Yeah, because ethyl comes before methyl. It just happens to be on the next carbon down. Then you need to tell somebody what the parent is. There are 8 carbons, that's oct, and it's an alkane. So, this is a real treat to pronounce, but if you're looking at the name written down, you can't write the wrong structure, right? We're staring at an alkane. We see ane. There's 8 carbons. I see oct. And then I have numbers associated with all the substituents, so I know where they are on the molecule. If I were to name this numbering from right to left, I'm still going to put it in alphabetical order, but I changed the number of the carbons now, right? So it's, if I numbered in this direction, 7 chloro, I have 4 ethyl. I now have 5 methyl. Octane. And you have to look at these and say, all right, well, I've put everything in alphabetical order accordingly. I have given this the correct number of carbons in the parent. I've successfully named this as an alkane. The difference between the 2 names is that for ethyl and methyl, I have both carbons 4 and 5, but only in the first option do I give a 2 versus a 7, right? So 2 is less than 7. So this right here is going to be the preferred name because 2 is less than 7. with all other things being equal, the only spot where I see a lower possible number is going to be for the chloro group in that first name. So that's how I would name that molecule. What are some of these common prefixes that we're using in our nomenclature? So we've been doing IUPAC nomenclature so far, but we did talk about constitutional isomers, and they come into nomenclature as common prefixes if they're alkyl groups. And it's totally okay because a common system for nomenclature can be sometimes a little different than IUPAC. In common nomenclature, we don't use numbers very often, but we do have common nomenclature for our alkyl groups. So these will be common prefixes. And we are allowed to use common system in IUPAC nomenclature if we're talking about an alkyl group. So for example, we could make a list of alkyl groups where there are different constitutional isomers, right? So I could have the alkyl group followed by its potential isomers. We could have the common prefix. That we would use in IUPAC nomenclature. So sometimes when we're naming functional groups, it'll be like, hey, the common name for this is this. The systematic name for it is something else. Sometimes you can be like, hey, I have an alkyl group that has a constitutional isomer, and I'm going to name this systematically, or in other words, I'm going to use IUPAC nomenclature, but I'm going to go ahead and use the common prefix, even though that has a different set of rules. And that's okay. It's been generally accepted that that's totally fine. Like the isopropyl group is a really easy example just off the top of my head. So the propyl group looks like this. So I've got CH3, CH2. Propane would have had a CH3, but I'm going to remove a hydrogen and I'm just going to put rest of molecule. So this thing right here is a propyl group. An isomer of that would be like if I moved R to the middle carbon, right? So I would have CH3, CH, and I'm going to move that hydrogen off of the middle carbon and put it on the end here where the R group was, and I'm going to move the R here. All of a sudden, I still have 3 carbons, right? But I have what's called an isopropyl. Oh, let me put that. I made a little category for this. Isopropyl. So a really easy example that people might be most aware of in your medicine cabinet, you have rubbing alcohol. So if R was a hydroxyl group, right, so an OH, and you had just a propyl group, right, it would be N-propanol. But if R was a hydroxyl group and it was sticking off of that second carbon, the one in the middle there, it would be isopropanol. So that's where we would bring in that common prefix. The butyl family has a few examples. So we've got N-butyl. So here's our N-butyl group. What if I moved one of these groups over, swapping out a hydrogen for the methyl group? So that has the same number of carbons, it has the same molecular formula. We have arranged these differently. Instead of a straight chain now, we have the isobutyl group. So if you notice that at the very end of the molecule, if you were to go from R and work your way to the left there, we have a terminal, meaning on the end, isopropyl group. And if you have that situation where you have a terminal isopropyl group, even if you have more carbons involved, like in this case, we have 4 carbons, not just 3. Anytime you have whatever number of carbons and you see a terminal isopropyl group like that, that little V-shaped thing, it's going to be called iso whatever. So in this case, isobutyl. You could have isohexyl, you could have isopentyl, whatever. You're counting out the number of carbons and you're going to use that prefix to let someone know. But if you use the prefix iso, it tells them there's a terminal isopropyl group. So this is isobutyl. It's also possible that we could take N-butyl and we could move the methyl group to the other carbon closer to R. So that would look a little different. It would look like this. So now R is here, and we move the methyl group over a little closer. So we're saying that now that R group is on a secondary carbon, right? So that carbon is going to be considered secondary if we're just looking at, hey, what R might be. Say it's a hydroxyl group, right? It would be a secondary alcohol. Or in other words, you have a carbon there that sports 2 alkyl groups, and who knows what R is. It could be another alkyl group, could be like just a regular old alkane. But in other words, we have R, and we're staring at the secondary carbon. Or in other words, R is on the second carbon in the butyl group. So we have a prefix for that. And we call it sec. So sec-butyl. So in this case, we have R, whatever that may be, is on the second carbon in the butyl group. And it could have been like a pentyl or a hexyl or whatever. And then we have, so let me highlight that. Your R group is now on that second carbon. You also have the option to swap out if you were to have, say, created the T-butyl group. So I'm going to cluster up all of the methyl groups. And now R is directly attached to that tertiary carbon. So this is your tertiary carbon, right? It has 3 alkyl groups or 3 substituents, and then whatever R happens to be. So this whole thing is considered to be a tert butyl group. So sometimes you might see these things abbreviated like T-butyl or S-butyl for this one. Sometimes we get really lazy and you might see something like this. a little superscript and then BU. Not often, but that one is sometimes seen for, like, if you have isopropanol or whatever, sometimes you'll see something like this. A little superscript and then a PR. So that's not something I'm saying, hey, I'm going to test you on that, like these little exceptions, but very often we use the best shortcuts that we can in these names. So if you happen to see a T-butyl or a little IPR like that, it's referring to the isopropyl group or the T-butyl group or whatever. And then for one other one that I can think of that it might behoove us to actually take a look at would be if we had just added one more carbon, like if I had N-pentyl. So I have a methyl group. I have 3 methylenes. I would have had a methyl group on the end there, but I'm going to remove a hydrogen, so CH2 instead, and then bond an R to it. So this is N-pentyl. I can write this a little differently, right? Just rearrange the groups, but keep the same molecular formula. So what if I put a methyl group here and created that terminal isopropyl group? So right now, right, that's an isopropyl group, but we still have 2 more carbons to go, and then R. So this right here, that isopropyl group, and then the 2 other to make it a pentyl, turns it into an isopentyl. I've got 5 carbons in the group with a terminal isopropyl. There is another one where I could hook up all of the methyl groups to one of these carbons. And then I have my methylene with the R group on it. So I still have 5 carbons in the group. They're just arranged a little bit differently. The common name for that particular setup, because remember, it looks a little bit like T-butyl, right? But I have an extra carbon, is neopentyl. Okay. So that's the general structure and a briefing on the nomenclature for our simplest hydrocarbons, the alkanes, fully saturated, right? We've learned about the condensed structure. We saw the expanded structure. It's not often that we'll be drawing the expanded structure. Sometimes it's nice to expand upon a section of the molecule where you're going to do some chemistry so you can see the bond breaking and bond making that happens. But often we'll be using either the condensed formulas or we'll be using line bond formulas. So the nomenclature is not, I'm not going to make it too complicated. You might have a molecule with 2 or 3 different substituents, but it's not going to be a situation where it's not going to be too convoluted. That's not what, this course is about. So can you name, a simple alkane? Can you name a simple alkane that has another group on it? Can you recognize these different substituents, these alkyl groups, and these common prefixes I'm giving to you because they are very commonly used even in IUPAC nomenclature. With common nomenclature, you're going to notice that we're not using numbers. That's for systematic nomenclature. The systematic nomenclature makes it nice and easy to figure out what's actually going on with the molecule. In the next video, what I'd like to do is, especially for alkanes, we have constitutional isomers that we covered today, but there are conformational isomers. All of these carbon bonds in alkanes are single bonds. And if you are not dealing with a ring, you have a situation where you can rotate freely. You can, if you have one of your model kits, you can build a molecule and see just how easy it is to rotate these groups around a carbon-carbon single bond. And you cannot do that in a ring, and you cannot do that in an alkene or an alkyne. So it's worth noting the energy associated with these particular molecules when we change their conformation. So we can go into conformational isomers. I also want to talk a little bit about cis-trans isomers when dealing with cyclic compounds. Cis-trans isomers are dealing with, hey, what direction are these different substituents facing on a ring? Is one of them pointing up and the other one is pointing below the ring? Or are they both pointing toward the same side of the ring? If they're both pointing toward the same side of the ring, like the top or the bottom, those are cis conformations. And if they are pointing in opposite directions, one's coming up the top, one's going out the bottom, then those are trans isomers. So that terminology we're going to need to learn about, along with a little bit of different types of strain and the energy associated with bringing groups a little too close together, or sort of creating strain associated with the angles involved of a ring with a ring. So that'll be the next video. And I think to spare you a third video, I might tack on physical properties and reactions of alkanes, because there aren't very many reactions with alkanes. They're pretty simple. They're not like super awesome in terms of their functionality. We could use them in polymer reactions. We can use them as fuels and combustion reactions, and kind of like the list ends pretty much there. So they're not the coolest of functional groups. So there's maybe just like one or two reactions that I'll show you, and I might just tack that on to the second video. So we'll have 2 videos for alkanes, and then we'll jump into our unsaturated hydrocarbons, the alkenes and the alkynes. And at that point, we'll introduce an actual piece of functionality that we can do some interesting chemistry with.